Well, hi everyone, and welcome to GeoHug. Thank you, Carmen, so much for being our special rock star today. So Carmen's been working with the Geological Survey of South Australia since 2011, working on characterising South Australia's regolith. Was that it?
Yeah.
Yes. And sedimentary cover, and is also heavily involved in teaching regolith geoscience as part of the high-profile National Exploration School Undercover School Undercover. There we go. So thank you so much for coming along. Over to you.
All right, so I'll share my screen. Well, thanks for coming along today. I'll share my screen with you in a second. All right, so this is my first GeoHug event, I have to confess, because we had always at the same time our what we call the quarantine event in the survey, where we all caught up and at the end of the week, especially during the times of lockdown, to exchange some geological ideas and also meet your colleagues online. So hence I haven't really had the normal time to catch up on this GeoHug. But since we are kind of not really in lockdown anymore in South Australia, I suddenly, my Friday afternoons are free, and I was more than happy to help out today to give a presentation of the work I've done in the last three years. So I'll take you today to the northwestern corner of South Australia, which is called the Palaeovalleys. So it's the land of the Ananu, of the Pitjantjatjara and Nanganatjara people. So the indigenous people still living there. Geologically, it's the Musgrave province. And I started to get involved about 3 years ago in a study that was overseen by the Goethe Institute for Water Research, with the main objective to find actually new groundwater resources in remote areas of Australia. And in their third phase of their research program, they focused onto the Palaeovalleys. They got a couple of organizations together, like the Department for Environment and Water, CSIRO, Flinders Uni, as the main players, and also the Geological Survey of South Australia, to help them out with finding new groundwater resources and develop new and innovative techniques to do that. And by that time, I actually then joined them, and because it was mainly dominated by people within the water sphere, I always say I brought the geology back into the research. And that ended up that we actually discovered evidence that in the Miocene, we actually had marine influences up to the foothills of the Musgrave Ranges. And the Musgrave Ranges are nowadays far away from the coast, and even in the Miocene weren't actually directly at the coastline, but somehow marine influence had to get there. And I'll tell you today the story how that happened. And while we were actually looking at that, we also discovered new groundwater resources for the communities in the Palaeovalleys. So I want to thank my co-authors and researchers who helped me to develop this concept I'm introducing to you today. So as I said before, I take you to the Palaeovalleys, the Musgrave province, give you a little bit of an overview of the geology there. So the basement rocks are made out of the Paleoproterozoic to Mesoproterozoic Bergscate complex that have been then later intruded by granites of the Pitjantjatjara supersuite. These kind of combine the basement rocks, mainly granite and gneisses, that then at later stage have been again intruded by layered ultramafic, mafic and off-site intrusions of the Giles complex, and various other dike suites, younger dike suites like the Alcara, Kolal and Amata. Then from the Neoproterozoic onward, really this province has been onled by multiple sedimentary basins. So the oldest being the Officer Basin, the Neoproterozoic Officer Basin, and then the Mesozoic Eromanga Basin in the west. And then during the tertiary, we have the formation of an extensive paleo drainage network, which is on that map shown in this purple. However, this drainage network of these so-called paleo channels have been really only inferred, and the extent as shown on this map has been mainly mapped from modern day surface pattern that people thought might reflect these ancient drainage systems. Another thing that's also interesting about the Musgrave province, that it's still tectonically active and has been throughout a long geological history, and that tectonic activity is actually reflected in some of these paleo drainage features I will show you today. So as we know in geology, it's always great when the rocks are cropping out, and in the Musgrave province we have the Musgrave Ranges. That also includes the highest mountains in South Australia, which is Mount Woodruff. And they're, you know, fantastic outcrops in a semi-arid to arid region. It's easy to actually understand your geology, to look for aquifers, or, well, you know, or looking for a flow path of groundwater or water, and then filling aquifers in the surrounding plains. But if you actually have to deal, especially outside the range province, with sand plains, geology becomes really hard to do. And one of the things to tackle that is using new or geophysical methods to actually look through that cover. And so in 2016, my government department, the government of South Australia, through my Department for Energy and Mining, supported actually the acquisition of airborne electromagnetic data. And that was mainly to increase the knowledge of the cover characteristic we have outside, mainly south of the Musgrave Ranges. And the reason to do that was to provide actually new insights into the geology, what's actually undercover, so the basement geology below, but also the hydrogeology and also the hidden ancient landscapes of these inferred paleo channels that have been mapped previously. And because paleo channels are always quite often connected with groundwater resources, was also by flying an airborne electromagnetic survey, will we actually find something out about potential new groundwater resources. And then in looking into the exploration sphere, you know, it's also, if you're in an area undercover, exploration is always expensive, and it's a bit of a lottery. So by actually understanding that cover, the depth of the cover, the composition of the cover, and actually what's below the cover, we can also help reduce the exploration risk. The Musgrave province is actually a potential area, really in South Australia, a greenfield area for nickel and copper deposits and platinum elements, as well as potential IOCG. So there's also a kind of exploration interest in that area, in addition to the groundwater. And groundwater, general water, can be used for mining, or if you want to actually develop mining in this part of the state, then you need water resources. But I think one more important thing of this research was also finding water for the communities that live there. It's one of the few places in South Australia where we have still Indigenous people living in their original homelands, speaking their original language, and they're quite large communities. So finding water resources for those communities is also really important. And another aspect in the APY lands is also water for agriculture, because they're good pastures, and cattle has roamed these vast sand plains for a long time, and the local community up there is quite interested of rejuvenating that industry. So kind of like, you know, lots of interest to explore what's within the cover and also below the cover. And in order to find that out, we use this geophysical technique called airborne electromagnetics. And for those who are not so familiar with what airborne electromagnetic is, and I haven't been either, I'm not a geophysicist, but so the data is gathered by transmitting an electromagnetic signal from a system attached to a plane or helicopter. And on the right-hand side, you see a helicopter with the SkyTEM system set up. And by flying over the land surface, it detects the variation in conductivity on the ground to a depth of several hundreds of meters. So most probably it's best within the field between 0 and about 300 meters, but in places, you know, it can even go down to, you know, 500 meters and more. And we get this, the conductivity response is caused because we have electrically conductive material in the surface, like salt or saline water, graphite, clays, or sulfides. And these cause this response in conductivity. So saline water or sulfides have normally a high conductivity response, and hence are then imaged from the surrounding areas which lower conductivity response. Normally then airborne AEM is flown in lines as parallel as possible. When you set up an AEM survey, you normally do that perpendicular to the structural grain. In this case, the overall structural grain in the Musgrave region is east to west, so the AEM survey was flown from south to north. As we can see in the left-hand corner of the slide with the red lines, they were about 2 kilometers apart. And then there were some infill areas, which are like denser red rectangular areas where, especially around the communities, where denser line spacing was flown. And what you then get is these conductivity profile 2D profiles that, as plotted on the map here, show you the conductivity response. And you already see these kind of V-shaped features that potentially could be linked to some of the palaeovalleys. The AEM data was actually processed by GA and then also by CSIRO, by Tim Monday, from which most of the AEM images I show you derived. And out of the data set, these 2D profiles, they actually model 2D depth slices that shows then the spatial variation of the conductivity throughout a landscape. So what came out of the AEM survey flown in the APY lens? Well, on this image, we see the depth slice at around 50 to 60 meters. That's draped transparently over the TMI, the total magnetic intensity image, that shows us really nicely the structure of the structures within the basement. But what actually became quite obvious when looking at the AEM depth slice, that there's clearly a pattern emerging. And when we look at the pattern, that reminds us of a fluvial system. So if you would actually draw a river system, you know, that's what this image really images. So the interpretation that comes to our mind first, that, well, at that depth below the cover at around 50 meters, we really see, thanks to the AEM data, an extensive paleo drainage pattern throughout that part of the APY lens. So it's one thing actually to see that, and you know, it shows you the conductivity contrasts quite strongly with high conductivity in these linear features in the red colors and lower conductivity in the blue colors. That, well, as a geologist, we would straight away say, look, these are fluvial patterns, and these are palaeovalleys or paleochannels that are submerged under the modern day landscape. But in order to actually really verify this data and what these features are, we actually decided to do follow-up drilling and groundwater testing to verify what we actually see in the AEM. And by doing that, then we could actually then go back to the AEM images and start mapping the spatial distribution of these palaeovalleys under the cover, and also depict where the deepest part of these valleys are, which we call the thalweg. Because that also means if you explore for bedrock, this is the part where the Palaeovalleyfi is thickest, and that's where you have to drill deepest, and you try to avoid these areas. And then based on that information, we plan then to compile a cover regular thickness map. And this is what we came up with. A quite old-fashioned looking map, and I think it's quite refreshing in these days of data and 3D models to see actually a good old looking map. However, all this data I show you today are also digitally available. So on this map, we see the extent of the palaeovalleys, the thalweg in the main image, and the depth slices of the AEM depth slices that were used to create these images. On the right-hand side, a little bit of a story how these palaeovalleys formed, and then the regular thickness map in these yellow and brown colors. And I could end here, but I think I will now talk you through how we actually developed this map and how this map came together, and actually how we unraveled the story. So from the whole data set, we actually then, from the whole AEM data set, we had to zoom in into one area to do the following up drilling program. And that was mainly determined by not necessarily exclusively the geology or the data, but also the proximity to existing infrastructure. So we needed these channel features crossing some existing roads and being close to an existing community, because if we actually find potential groundwater, new groundwater resources in these palaeovalleys, we want to make them available for the community, and the further community is away, the more expensive it is to develop these groundwater resources. But also it's in these areas, it's also with access and clearance, it's always closer to have it to exist. It's always easier to get clearance to do your drilling programs if you're closer to existing infrastructures and roads. So then we picked an area around in the vicinity of the community called Kalchichi in Frigon, and put down 11 wells, focusing on two areas. One in the middle of this Palaeovalley trunk we see here, crossing the road in black. I don't know if you see my cursor, but where the white circle is, that was our DH1 area. And then we had an area a bit outside the actual Palaeovalley, so went into the interfluve areas, and that was the site DH22A. I'm only talking today about DH1, where the Palaeovalley is about 1,500 meter wide and about 100 and 150 meter depth. Well, that was before we actually drilled. That was these dimensions derived from the actually AEM data. So the other thing is also we wanted to find out with the drilling was what's actually the composition of these valleys. There have been concepts developed how they look like, sometimes based on some really rudimentary drilling. To date, there's only really this drilling program that actually targeted these features. Normal water wells are in existing drainage or creeks. They are offset from the main palaeovalleys, and hence there isn't actually any existing drill hole up to the time we then started our drilling program into these Palaeovalley features. But with the AEM, already with this north-south cross-section, we find that there seems to be some compartmentalization within this Palaeovalley based on the conductivity. Not super exciting, actually quite a straightforward layer cake potential stratigraphy. And then we decided we go into the deepest part picked by the AEM data and actually following up what that fill is like. And also to confirm the exact contact between the underlying weathered basement and the overlying Palaeovalley. And we did that by coring through the center of the Palaeovalley. And this is the first and most probably the only core you will ever see in your lifetime from one of the Palaeovalleys in the APY lens. I've fought really hard to get this core drilled, because generally if you're drilling for water, you're going just for drill chips. But I think, as I always say, if you spend $2 million doing a geophysical survey, it's actually worth to spend $30,000 drilling a core through one of the central parts of what your data is imaging. So yeah, so it was the first, and we also gained really lots of information from that core. And it also verified that sometimes an additional investment in taking cores through the cover sequences can turn out really, really well and helpful. So what I'm doing now, I will talk you through the core and talk a little bit about the sediments we find in these cores. And by that, unravel actually the story of these palaeovalleys, how they formed and how they were filled, and also where we find water in them, because they're actually full of water. So overlying the weathered basement, we actually have all the fluvial deposits we see here. They are like quite medium to coarse grain sandstones at the base, and you can see quite quickly they're filing up and becoming quite massive, strongly consolidated sandstones. And that interval also correlates to the AEM flight line, or the AEM cross-section in this kind of medium conductivity. So on the left-hand side, I actually have the lithology log with the interpretation of the deposition environment, and then the AEM flight line, and the different colors again show the different conductivity, with yellow being lower conductivity and purple being the highest conductivity. So moving up into the zone with the highest conductivity, and what we actually encountered here in the drilling were like black muds, separated by a 1 meter thick gypsum layer, and then followed by more like green gray muds. And so we had a quite easy explanation what this high conductivity layer we see in the AEM cross section, and also here in that profile reflects is actually a thick, it's about a 20 meter thick mud layer that's composed of like pyritic dark muds, mudstones, or yeah, well actually not mudstones, they're really consolidated muds, and then towards the top more these greenish ones. The interesting thing is this 1 meter gypsum layer in the middle, because normally mud, fine-grained material is either deposited in the deep ocean or in lacustrine settings, like in still water environments. However, if you get actually a gypsum layer in between, it also means your water body at that time had to dry out. And so that already gives us a bit of an idea of fluctuations and change in the deposition environment throughout the time. So we're moving from a fluvial deposit into a lacustrine deposit, where we actually had wet phases and dry phases. However, we then decided actually to sample some of these muds, because normally if you see black muds, there's a good chance that you can get some paleonomorphs out of them, and by that can do some palynology and find out something about the deposition environment and also about the age of these deposits. And by doing so, we actually discovered, or my colleague Liliana Stoyan discovered, that we have actually dinoflagellates, which are indicative of a marginal marine environment. And this is where the sniff of the ocean comes in, which I included in the title. So suddenly, before I was interpreting as just a fluvial lacustrine setting, we see in this interval, in this mud interval, actually some influences of some marginal marine flora, and that means also there must have been some marine waters in incursion into these palaeovalleys. So there seems to be a bit of a marginal marine brackish fluvial intervals, switching back and forward throughout that interval. The age of these polymorphs also indicated to be that this is most probably around Miocene, mid-Miocene age. So that gave us actually the first time an age control about how old these Palaeovalley sediments could be. Moving up in the sequence, then we're shifting again to more fluvial deposits, actually now into the fluvial deposits of a younger phase of fluvial activity within these palaeovalleys, and the deposition of sandstones that are partly overprinted by calcium carbonate. And then moving higher up, we're getting more and more carbonate overprint, and we're switching then into coming to the top of this Palaeovalleyfi, and the deposit and then deposition kind of changes into what we see today, with extensive sand plains, aeolian sand plains, fluvio-aeolian sand plains. So if you put that together next to each other, to recapture what we actually saw was we have these older fluvial deposits, and most probably older than 10 million years ago, then followed by this thick mud layer that shows indication of estuarine or marginal marine influences, then a switch back into the younger fluvial deposits, and then the change into the more modern day, environment with fluvio-aeolian sandplain deposits. while drilling this core and then following up as a water well, we actually discovered also 3 main aquifers, one within the quaternary succession. So it's indicated by these blue bars on this graphic. And then one just above the big mud layer. And then one actually within the weathered basement, just at the base, below the base of the Palaeovalley contact. All of that water is quite fresh with quite high flow rates. And so that was actually quite a good story. But I also show you now a bit of like in a cartoon, it's like what we see in the core in a kind of a semi 3D reconstruction, landscape reconstruction. So there was a time before actually these valleys were filled, they had to be formed. And this formation of these deeply incised valleys happened most probably in the late Mesozoic to the earlier Paleogene. So, you know, 65 million years onward. And it's actually quite interesting because these valleys are more than 50 meters steep. So they're quite steep valleys that are carved out of the most probably by then already weathered basement. And the interesting thing is that they actually cross the overall geological strain, because we saw the main structures in the APY lands or in the Musgrave province are actually east to west. So they're cross-cutting actually through that and actually flowing to the ocean in the south. Yeah, so then after the first deposition and after the valleys actually have been formed, they have been filled by the first phase of fluvial deposition. And that was then followed by this incursion of the marine incursion. So that doesn't mean that we had actually the ocean and the coastline directly there, but what it actually means, we had these deep incised valleys and they have been backfilled, and the marine waters could actually fill back, so that I must have quite high sea level that they filled back really that far inland. And I was thinking of an analog you could use for that. It's most probably think of the Norwegian fjord system under a semi-tropical climate. This is most probably what we're looking at. We have large valleys that are going back inland for several hundreds kilometers, but where, because of fluctuations in the global sea level, they can be actually filled back, and marine waters, and by that also marine floras and environments, could actually be deposited that far inland. And to clarify that point a bit, because I think that is really quite exciting, we have here the Eucla Basin, which was at that time the coastline for these valleys emerging from the Musgrave, flowing to the south. And so we are at this DH1A. This is the location we did the drill hole. But there's also other drill holes, Officer 1 and Man 1, where we have evidence of this Miocene marine influence. So we could actually now, by adding DH1A, we could actually add the extent of the marine influence during the Miocene inland into South Australia. So these palaeovalleys we see here were actually more like a large estuarine system at that time. And it's just a kind of like a little zoom in on that. Yeah, but within this thick mud succession, we also have indication of drying out. So there must have been quite a bit of a reversal between freshwater and marine environments, but also also ongoing with some climatic changes, because with the drying out, you most probably need a bit more times where the climate also got drier. And then that was followed by the second fluvial deposit fill, where most probably more rain happened in the Musgrave Ranges and deposited all the sands being washed away and filling this valley up. By that time, at the end of the late Pliocene, these deeply incised valleys have been completely filled, and then and also with the continuous drying out of Australia, we switched into these more sheet-like sand plain deposits with dune fields developing. and forming today's landscape, which we see here on this figure. What I also want to point out on this figure is the modern day creeks. They're actually offset from the center of the ancient palaeovalleys. Normally when people did groundwater exploration in the Musgrave, they drilled next to or within the modern day creeks, because that's where people think the water is. And however, these creeks are often like 2 to 5 kilometers away from the actual axis of these palaeovalleys. And hence, these palaeovalleys haven't really been drilled because they're just sitting under the sand plane and are not really visible. But because we have now the AEM data, we can actually now really pinpoint to where that is. And we also found out if you drill into the center of these palaeovalleys, if you know where the center is, this is also where you find the higher water flows and the better water quality. So by now having a bit of control about what's the fill of the valley, where's exactly the boundary between the underlying basement and the base of the Palaeovalley, we could then actually decide on the depth slices of the AEM that will help us actually mapping the top of the Palaeovalley extent and the base of it. And the top was around 30 meters before we switched from the second fluvial fill phase into the modern day sand plain deposition environment. So if you look below 30 meters below the surface, we actually see the top of the deposits within the Palaeovalleys, and by that also the margin of the original incised Palaeovalley. And by mapping then that, you can actually then really define where the Palaeovalley starts if you start to drill down from the surface. And then by knowing that at around 110 meters, we have the contact between the base of the Palaeovalley and the underlying basement, we can also then start using that depth slice to reconstruct the palaeothalweg, so the deepest part of the Palaeovalley. And again, this is important for groundwater exploration, because if you explore for groundwater, you want to sit directly on top of the sweet spot on your sand plane to start your drilling into the aquifers, because they're best above this thalweg. If you're exploring for the bedrock, then you most probably want to be outside that thalweg, because that's the deepest cover, and you actually want to avoid that because drilling is expensive, and the thicker the cover is, the more you have to pay. And so CSIRO used some machine learning techniques within the AEM dataset to then extract these or the deepest points of the thalweg. And by combining all that, we actually managed then to put that all together in a map and in the dataset. So to conclude, the AEM for us proved really be essential for identifying the location and spatial extents of where these palaeovalleys are. It helped us mapping the Palaeovalley thalweg. And there is another important thing for exploration and also the geological understanding, which I haven't had much time to talk about today, is the relationship between structures and the Palaeovalley evolution and the fill. That's maybe time for another talk one day. And then the drilling that proved to be essential in respect to actually helping to ground truth the AEM data. Even if we only did that in one point, but from that point, we have actually now some really good control to apply that information to the rest of the data set. The drilling was also essential for verifying our geological interpretation of the AEM data, determine the Palaeovalley thickness, their compartmentalization and their composition. And it helped us determine where the weathered basement and Palaeovalley contact is. And despite all of that, we also found a new groundwater resource for the people in the APY lands, which I think is great. It's now up to them to decide how they want to use it. We've done also some dating of the groundwater, and it's less than 10,000 years old. So for some people, that's quite old groundwater. If you look at the area, it's most probably still on the younger side of groundwater we have in South Australia. So that also helps with planning the development of these aquifers for future generations. I want to thank the people of the AP Islands for letting us on their country and work with us, and all the other people involved in making this project happening. Well, thank you. That's the end of my talk.
Thank you so much.
Can I ask a question?
Sure
Yeah.
can.
Carmen, nice story. Thank you very much. Two questions. Now, you probably answered the very first. 10,000 years old, it must mean that it's obviously not been recharged, right?
Well, I had that discussion with my colleague from DU. So it depends on how fast it travels to the area. You know, so you're right, it's most probably very slowly recharged. But the recharge point from the drill hole is most probably about 70 kilometers to the north. Also, so you're right. So, but that also then means that's where it's then really important is like, do you actually want to develop these groundwater resources? Because, you know, if you take them all out now, it will be a long time before they will be recharged again.
So was there any estimate of the volume available? I mean, we obviously, if there's someone finds some sort of mineral resource not terribly far away that requires water, you'd have to have a substantial resource of water to be able to be of any use.
Yeah.
Any idea as to volumes available for such a situation?
No, I don't. I can tell you that we had actually in the upper aquifer, we had flow rates of 20 liters a second. And that was actually quite a lot. And if you actually think the Palaeovalley in this place where we drilled was 1.5 kilometers wide, and the upper aquifers, you know, it starts about, you know, it starts around 10 meters below surface and it's about 10 meters thick. We actually get, even on that spot, quite a bit of a big value. I think the problem often I found with this project is, and it's a bit of a sad side to the story, is we often do the data collection, especially for geophysics data, and these really large regional areas and cover really a lot of ground, like, you know, Geoscience Australia has done now with the Exploring for the Future program, which some really great AEM data for the whole northern part of the of Australia, and hopefully finishing the south off in the next phase. But it's often the follow-up where there is really limited financial resources to do. Again, this whole interpretation, you know, sits around, we had 2 drill cores, but one was outside the Palaeovalley, or actually in a tributary. And originally I would have loved to do like at least 4 or 5 along the main trunk of the Palaeovalley to see what the variation is. So again, you know, this, I guess the AEM data shows us there isn't within the Palaeovalley field, there's much conductivity changes. As you can see from the whole data set, when you look at the depth slice, it's quite consistent. And you know, that's a nice thing about it. The data set, and it's such a really good AEM data set. So Tim Monday, who works with quite a lot of AEM, is always quite delighted about the AEM data set from the APY because it's so clear. However, you know, that may apply to the actual fill and the sedimentary fill of the Palaeovalley, but not necessarily to the aquifers, because the main conductivity contrast doesn't come from the water because it's actually quite fresh. So there's actually not, we didn't come across really saline water, but it's more about the sedimentary fill. So this mud interval that seems to be really quite extensive throughout the whole Palaeovalley system. Another thing I haven't spoken about, but what actually got, at the beginning, I was really exciting to get a drill core through sediments, and I thought, oh, there were all these great sedimentary structures, and you know, I love my cross bedding, and it was actually, there was an absolute lack of sedimentary structures, and I wonder why that was, and and hence the actual fill wasn't as compartmentalized as I thought. It's actually like a layer cake stratigraphy. And that's mainly because the catchment area, it's the granite and the gneisses, which if you weather them deeply, they weather to Kl9, and then you have some quartz left. And the quartz has a quite similar grain size than all the individual minerals. And then you don't have to transport them fast to actually break them down all to the similar grain size. And by that, you get actually quite a homogeneous sediment. And so at the end, it's actually 2 piles of medium grain sand stacked on top in the middle with a mud layer in the middle. And that was quite surprising for me. I thought we see more evidence of, you know, I can tell something more about the fluvial style and that, but it's like moving sand from A to B and getting rid of the clay on the way.
The drainage system doesn't seem to be extending right up to the hills per se.
Yeah, that's right.
And which is a bit strange, because if had they been, and it may have given you some idea via the geochemistry whether there are some interesting potential sources of mineralization in the Musgraves.
But at that point, when these valleys formed, the foothills were much further south.
Yeah.
And the other thing is also that we find, especially in that area to the north of Calcite, these palaeovalleys start actually south of these large east-west shear zones. So it seems that water flows more as a sheet and then is concentrated and funnel once they hit the shear zones, and then kind of cross them and form more this dendritic pattern. And every time there's another fault or shear zone the valley crosses, there is actually a response of the fluvial system by bending. So we have then meanders or kind of breaking and this being displaced. And we see that also in the modern day channels. And that's why at the beginning I said, you know, the AP wildlands is still an active, tectonically active province. And there's still influence of neotectonics on the modern day drainage system, but it has been on the Palaeovalley drainage system. The good story for exploration is here, if these are, you know, highly active shear zones, and if there is some mineralized rock in the subsurface, these are most probably fluid pathways to the surface. And that would be a good story if you start doing surface geochem surveys over there to actually explore for signatures in the cover. So we hope with so I don't know if you guys know, but Geoscience Australia has announced the Exploring for the Future program #2. And they just announced the 2 areas, the 2 legs that hold Australia. So it's actually along the South Australian, Western Australian, Northern Territory and Western Australian border one. And then on the other side of on the eastern border of South Australia, straight up to Northern Territory. Okay. So we hope that actually, then, you know, one of the hopes for us in South Australia is extending the AM survey to the Western Australian border and across, because Aus Minerals, for example, they are starting to develop one of the mines on the in West Australia, on the West Australian side of the Musgraves, and so that whole water story will be quite important there too.
Thank you so much for your time. Been very generous, so thank you. And yeah, thank you for presenting. That was really, really interesting. So thanks everyone for coming along. I hope you have a great weekend and see you next Friday.